In this question, they're asking us to link the free energy change of a reaction to electrochemical cells. The equation that allows us to link free energy change is this one. It involves Faraday's constant. So just a couple of things. The N is the number of electrons transferred between the two half reactions. To find that, you've got to get to a point in adding together the half reactions that you know the coefficient in front of the electrons just before it crosses out. That's the number of electrons transferred. We'll see that in a second. And then secondly, F is Faraday's constant. It tells us how we can relate the amount of charge to the number of moles of electrons. And as it turns out, there is 96,485 coulombs of charge for every 1 mole of electrons. Let's take a look at problem A. We can see that we've got zinc becoming zinc ion, and we've got silver ion reducing to neutral silver. If you go on a table of standard reduction potentials, you can look these both up. The reduction reaction will appear exactly as it is, and you get a voltage of 0.8. The oxidation half reaction will appear flipped around in a table of reduction potentials. After flipping, it's a positive 0.76. When we add these two half reactions together to get the total voltage and the total overall equation, we have to make sure that the number of electrons crosses out. So we've got a 2 in the oxidation half reaction. That means that we need to double the coefficients throughout the reduction half reaction. Doubling coefficients in the reduction half reaction does not change the voltage. It stays at 0.8. So if we add this through, the electrons go away, and we're left with neutral silver and zinc ion. On the product side, the voltage is a positive 1.56 volts, which would have to be the case if it's a galvanic cell. Okay, crucially, that number of electrons, the coefficient in front of the electrons, is the value of N. In this case, for problem A, the number of moles of electrons transferred is 2. The voltage, the standard cell potential, is 1.56. And then the last bit to apply the equation is just Faraday's constant. So we'll apply the equation. -2 times 96,485 coulombs of charge for every mole of electrons times 1.56. And instead of writing V for volts, I'm going to write the constituent units that a volt is. It's a joule of energy per coulomb of charge. It's a ratio of energy to charge. And that will allow us to cancel out coulombs. When we multiply this through, we get negative 301,033 joules is a unit that's not crossed out, and per mole. WebAssign wants us to convert that into kilojoules when we write our final answer. So the unit after the answer blank is kJ, kilojoules. So we'll divide by 1,000 and round to a reasonable number of significant figures. Negative 301 kilojoules. And there's nothing wrong with writing kilojoules per mole. That's completely fine, as we had done throughout our thermodynamics study. You can put the per mole or you don't have to. Okay, problem B. In problem B, they give us the half reactions directly. That's helpful. They're both written as reduction reactions. So notice the 2 electrons on the left side. We have to pick one of the voltages and the reaction associated with it to flip around, so that when added to the other voltage, you still get a positive result. In this case, we'll flip the one that's on the bottom, the 0.68. And you know what? Let's do this a bit of a shortcut. We don't have to, in order to apply our equation, we don't have to have the overall reaction. We do need to know the number of moles of electrons. Thankfully, they match, so we don't have to do any multiplying of coefficients. So n is 2 in this reaction. And if we can look closely at the voltages, a 1.78 volt half reaction, when added to a 0.68 volt reaction after it's been flipped, is a negative 0.68. So to get the overall voltage for the cell, 1.78 minus 6.8, that gives us 1.1 volts. Let's remember that as we carry on our calculation down below. There we go. Okay, so problem B, same equation as before. In problem B, it was 2 electrons, n was 2. Faraday's constant won't change. 96,485 coulombs of charge per mole of electrons. And then our voltage was 1.1 volts. And I'm going to write the volts as joules per coulomb so that we can actually see coulombs getting crossed out. When you crunch the numbers, this one works out to be negative 212,267 joules per mole. And if that rounds to the nearest thousand, we would get negative 212 kilojoules per mole. And that would be the answer.